Hello, and welcome to the second part of our SDN training. As I've promised in our previous video, we'll continue by exploring control plane separation kind of SDN in a deeper detail. But before we continue, I'd like to spend a moment to remind you that SDN acronym is somewhat misleading how it is used nowadays, in a way that the most radical and the most famous kind of SDN is still in an infancy state. And while we will be exploring the control plane separation kind of SDN in our future videos, be advised that there are many other ways to build an SDN. So what is control plane and the complementary data plane? Well, the Forces Protocol paper explains it in much deeper detail, and it serves as a foundation for the Linux kernel networking model. But let's spend a minute discussing what functions and responsibilities the control plane and data plane have. Well, the traditional design for all modern networking devices have this kind of segregation of responsibilities. Data plane is most often a hardware-implemented, hardware-accelerated forwarding, or the so-called fast path of the device. And control plane is a set of functions and software applications that work on top of this hardware, trying to manage the network state, the information that is available to the switch, build the topology awareness, collect network lists, routing state, and all that to be used to manage what should go where. The design is very robust and inherently almost unlimitedly scalable. Each device works as a separate brain with its own conscious and subconscious processes, and there is no need in any higher level management entity. So what functions does control plane have? Control plane is a collection of applications in its essence that runs on top of a network OS, and it is responsible for everything network state related. It has to manage resources of the device, keep up to date the information about networks available, or for the switch MAC addresses that are reachable, perform ARP learning and or MAC learning, run all the helper algorithms and protocols such as STP, OSPF, and so on, and do all the other higher level management and control functions. For example, bundling links in a lag group, or running some sort of a heartbeat between a number of devices, or a lot of other vendor-specific or platform-specific functions. All that is control plane. So you can think about control plane as a consciousness, ever seeing and ever knowing, and keeping every memory in its place, the management body of your device. Data plane, by contrast, is a much simpler but immensely faster entity. It is a subconsciousness of our hypothetical brain, and is responsible for everything related to actually pushing data forward. It is responsible for QoS functions, access control functions such as filtering and logging, tunnel encapsulation or decapsulation, encryption or TCP offload, and everything that is related to byte crunching. So the data plane is actually what does perform the job, but without the control plane guidance, data plane would be clueless which flow goes where or what should be performed on the given data stream. And naturally, these two parts coexist in a very harmonic union. Most often when we configure something or perform any other CLI job in our device, we communicate with the control plane application or applications, and data plane is something that receives instructions and guidance from those applications later. It is quite trivial to check how actually data is being transformed from the higher level understanding of our, say, topology information to the actual IP routing table, and from that to the forwarding table, what is being used by data plane. Whatever higher level protocol you use, be it a switch or a router, the data is transformed by internal interfaces to a lower level, first IP routing table, and finally the actual table that is used by data plane, IP forwarding table. It is very easy to see and compare these tables in any modern device, and this architectural approach can be considered to be a traditional one, although it is quite new and is not older than, say, 10 years. And here comes a logical next step in our device's evolution. If we have a separate entity that has a clearly defined interface, why don't we run this interface over the net? Why don't we make this entity remote? That is the essence of control plane separation paradigm. That's the only difference from our traditional design, but this change actually introduces a lot of new benefits as well as some problems to boot. So what are actual benefits of having a separate control plane? Well, for starters, we have an additional abstraction layer. Very much like infrastructure automation nowadays, we can allow applications to work on top of a single presented API and or to work without knowledge about the network infrastructure topology or the number or type of devices, only caring about what is important to this application. And the SDN controller, this abstraction layer, becomes a thing that will transform your application needs and policies into a lower level rules to be installed among the devices in the net. With this together comes an elimination of redundancy. When we had our devices separate and independent, we were required to run some sort of a communication protocol between them, be it OSPF for routing data or STP for layer 2 connectivity. Anytime those devices need to interoperate, they will have to communicate between each other. Now, with having a centralized control plane, we don't need to run these protocols at all, because every new SYN network or every port state change will be reported to the single software, to the single operating system that runs on top. And while this will be remote and the delay may be considerable, still it allows us to keep all information in one place and operate on this information without running additional CPU cycles to, well, communicate between the devices. In terms of both human resources and infrastructure expenditures, it becomes cheaper to build such a network and later to manage it. Finally, what about the innovation? Well, it is here. When we have concerns separated and two pieces of our network working independently, we're free to run, say, a device's upgrade without ever restarting our control plane, or do control plane upgrades without changing the devices. So with this sort of independent evolution, it becomes so much easier to experiment and write new innovative applications and services on top of your network. So let me hit you with a brick of code in the end. This is an example of a controller code that tries to replicate a regular learning switch behavior. Developer here is using, well, it can be seen Ruby language, and this block of code is a very succinct representation of how learning switch usually behaves. We can see how for any packet that comes in, that's a function, packet in, We remember in our MACs table, for this packet MAC source address bound to its import, we basically remember port we got this message in, and then we try to search the same MACs table for MAC destination address to get our out port for the given flow. Finally, there is a send flow mode add function that is basically an install the rule command to match everything that is the same as the first frame in this flow and to act by sending everything that is matched out of the out port. Very simple, but it shows you the power that is given us by this kind of paradigm. Having control planes separated, we can take it apart, and after taking it apart, we can not only configure how our device should behave, no, we can change how the device understands network around it, how the device actually performs routing or switching, how it sees MAC addresses, what information it gets from the frame it receives, and all other lower level functions that up to this date were hidden. You can take every protocol apart. You can change all the inbuilt behavior if you think that you know better. And that's how this fourth kind of software-defined networking, and that's how OpenFlow protocol appearance have changed how we engineers can work and interact with our networks. That is why OpenFlow is being considered to be a revolution by some people. And the revolution happened in data centers first. Traditionally, the data center network is managed by a single entity and contains a huge amount of similar devices. It is a perfect place for SDN. It is a perfect place for lots of different kinds of SDN, but control plane separation is a perfect fit as well. Having a separate, centralized control plane to all these devices and having all the devices abstracted away, we can actually manage our network as a single thousand and thousand ports switch and just configure rules and policies without ever worrying about how the data flow will be going and which path is blocked or not. That will be managed by SDN framework. But while data centers are indeed a perfect place for SDN, other networks can benefit from it too. I will leave it to you as an exercise to think how wonderful it would be to fix your personal pet peeves and change the protocol behavior in places you'd like, or even just create your own type of network from the ground up. Replace it all from layer 2 up to layer 4 and make it work as you want it. Be it an ISP with a custom kind of tunneling, or your enterprise network with dynamic and flexible policies, SDN can benefit all of us. Is it all sunny and happy as it seems? No. Unfortunately, there are challenges to SDN, and specifically challenges that are connected with a remote and centralized control plane. First is, of course, scalability. In networks, we have to always consider the possibility of growing networks larger. And while the traditional design is almost infinitely scalable, having a central control plane application imposes a big set of requirements to the location of that application, its architecture, hardware it is working on, and so on and so forth. We have to make sure that the latency between data plane and control plane is not too big for your services, and the response time for every new packet coming, for every new question to the control plane is not too big. Then, of course, we have to manage trust, responsibility, and access to all the network. Previously, you had to manage, well, separate passwords or keys to every device, but now there is a single CLI or single GUI, and it is very different and somewhat more difficult to keep responsibilities separate. Then there is a requirement for reliability. When one device in the traditional network fails, its neighbors will recalculate state, send updates out, and network will keep working with probably some local small blackouts. By contrast, having a central control plane makes us always feel a step from a disaster, from losing the whole network via failure of a control plane that manages it. So naturally, we have to ensure that network will keep its probably most basic functions still running even on control plane failure. To these three issues, answer may be clustering. We can make a cluster of control planes, like a cluster of databases. We can create proper application code, but with that comes a problem of consistency. It's a very natural way of thinking, and of course, developers all over the world are trying to solve the same problems for different applications, but for SDN it's also a challenge. If we will be having a number of controllers, we have to make sure that they have a consistent view on the network. Basically, we have to find a sweet spot between keeping every device with its own control plane and having a single central control plane. Be it 3 or 4 centralized separate control planes, you actually may need to run OSPF or some sort of OSPF between them to guarantee that the state is consistent. The last but not the least is an interoperability challenge. While OpenFlow is the only protocol to manage these simplified dumb devices, we have a number of frameworks, competing frameworks, that work on top of OpenFlow and offer, unfortunately, not very interoperable APIs to higher level applications. Now, Open Daylight may be a promise of this common interface. It's an open source project that tries to pull all the vendors' resources and devs across the globe to a common goal, to develop a framework that will be that common abstraction layer and will offer a set of API hooks for all of us to use. Well, will this promise be fulfilled or not? It is yet to be seen, but currently we have a number of competing projects that fill the same niche. You've already seen excerpts from the Trima controller code, and we'll have a separate video discussing all other controllers out in the market. And in the end, I see it as a good thing. I see it as that sort of a Darwinian ecosystem that is finally here. I hope that in the end we'll have a striving jungle of applications competing with each other, and that we as users will be sure that we can always find something to pick for our network to use. That's it for this video. And in the next one, we'll start shifting from a purely theoretical discussion into a more practical exploration of how OpenFlow protocol works and how we can actually use it in our application. Thanks.